Okay, so we ran out of time in 8th period, so I wanted to make a quick video just reviewing on how to assign oxidation states. And so first of all, just a reminder of what an oxidation state is. An oxidation state is what the charges would be if all the interactions between the atoms were ionic. In other words, if we split where the interaction was along the middle, and therefore any electrons that were spending more time around one element than another, we would then just assign them to that element. Basically, anybody who has the higher electronegativity then will end up with the more negative oxidation state. But again, these are not actual charges necessarily, right? All charges are oxidation states, but not all oxidation states are actual charges. So if you have a charge of an ion, it's simple. It's just that's its oxidation state. But if there's not an actual charge, then we do this splitting thing. So for example, if we take our water molecule here with its overall dipole, if I were to split it right here, right, that covalent bond, there's not actual ions here, right? The electrons are spinning probability between the two atoms. But if I were to split it and assign a charge to whoever had the greater share of the electrons, time and attention, then that would mean oxygen would end up with the electron and hydrogen would lose an electron. So I say that the oxidation state of hydrogen is +1. And again, we've said this before, but notice that I write the positive sign before the numeral because it's not an actual charge. If I split the other covalent bond, then I get the same thing. Between that oxygen and that hydrogen, it's spending more time around the oxygen, and so I would say that hydrogen lost it, so it has an oxidative state of +1, and as a result, oxygen gained 2. So it ends up with an oxidation state of -2. Now again, these are not actual charges because it's a molecular compound. The electron didn't actually change hands. But to determine its oxidation state, we treat those interactions as if they were ionic. And if you split it and give the electron to whoever had the greater share of it, then these are the resulting charges that would result if it happened. And so those are oxidation states. All right, so let's look at another example. Here we have the diatomic molecule oxygen, elemental oxygen. If I split that double bond, then was there a polarity here? Were the electrons spending more time around one oxygen atom than the other? Well, no. And so if I split it evenly, then they both end up with the same share of the electrons, and so they both have an oxidation state of 0. That's true of all elements, right? All elements will end up with an oxidation state of 0 because there will be no difference in their electronegativities between the atoms, and so splitting them would not result in any resulting charges. What about this one? We've got carbon tetrachloride. Well, if I split those bonds, chlorine is more electronegative, so for each of those pairs of electrons, chlorine comes away with 1. Carbon, as a result, would lose 4 and become +4, and each of the chlorines become chloride ions with a -1 charge each. And then notice, and this is a good time to point this out, notice that the sum of the oxidation states has to equal the total charge on the molecule or ion. In this case, they're all zeros, but if it were an ion, which we'll see an example of in a second, it has to equal the total charge. That sounds familiar, right? That's just like formal charge. You'll see a lot of similarities between formal charge and oxidation state. All right, if I were to have CCl4 just written out like this, I could predict what I just showed with the diagram by thinking, okay, well, chlorine's more electronegative, so I know it's for sure going to get an oxidation state of negative per atom, and there's 4 of them, so it's going to be a -4. And because CCl4 doesn't have a total charge, that means the only carbon atom must be accounting for the +4 oxidation state. All right? Okay, now what I've done here is I've given you an example of a reaction. And the question is this a redox reaction? Well, the only way we know that is to find out whether anybody was reduced and if anybody was oxidized. And that will only happen if we see a change in their actual charge or their oxidation state. And so whenever you see something like this, you want to start off with the pure elements. because I know, like we saw a second ago, there's an equal sharing between those hydrogens, and so elemental hydrogen definitely has an oxidation state of 0. And I can say the same thing about the elemental chlorine. That chlorine molecule has an oxidation state of 0. There's equal sharing. If I split it down the middle, nobody gets a charge. So those have oxidation states of 0, as will all pure elements. So now I just want to take the next one that's easy to figure out. And we just saw CCl4 is the easiest to figure out because chlorine is so electronegative, he always wins, right? So he gets, well, I guess unless he's battling fluorine or nitrogen, oxygen, something like that. But in this case, he's battling carbon. So he's more electronegative, and so he gets the -1. But there's 4 of them. And so as a result, each chlorine atom has an oxidation state of -1, and the single carbon atom has an oxidation state of +4. Now, I point that out, and I do that one first, because that helps me recognize what happened to chlorine. Well, chlorine had an oxidation state of 0. It now has an oxidation state of -1. If you go from 0 to -1, you have gained electrons. And if you've gained electrons, then you are reduced, right? And so chlorine was reduced in this case. Well, that helps me figure out, well, if somebody was reduced, somebody else had to have been oxidized. And so hydrogen, which is kind of a squirrely guy, right? Sometimes he acts like a metal, sometimes he acts like a non-metal. I can look and I see that he ends up with an oxidation state of 0. Well, then he must have been what? If chlorine goes from 0 to -1, it gained electrons, then hydrogen must have lost electrons. And so if it ends up at 0, it must have started off with a -1. So each hydrogen's -1, and that predicts that carbon was a +4, which doesn't surprise me, right? It has to be a total charge of 0, and so carbon actually doesn't change oxidation states, but hydrogen does and chlorine does. And so this is a redox reaction. I can identify that hydrogen went from -1 to 0, so it lost an electron, it was oxidized. Chlorine went from 0 to -1, it gained an electron, it was reduced. And then sometimes we ask different questions on this. Sometimes we ask which element was oxidized or reduced. Sometimes we ask which reactant. So make sure you read the question. For example, if I asked which reactant was oxidized in this reaction, you would say CH4, methane, right? In other words, the hydrogen element was the element that was oxidized, but in terms of the reactant, you start off with CH4, so CH4 is the reactant that was oxidized. All right, one last example, an ion. If we have sulfate ion, it has an overall charge of -2. So the sum of the oxidation states has to be -2. Well, between sulfur and oxygen, who's the easier one to predict? Oxygen. Oxygen, always -2, right? Super electronegative, and in group 6, and so it's a -2 oxidation state, and there's 4 of them. So all 4 of them together at their -2 will make a total of -8. Well, if we have -8 on the oxygens and a total of -2, an actual charge of -2, then the oxidation state of sulfur must be +6. All right. So this is just, again, a review of what oxidation states are and how you would predict them in molecules and ions. All right. Study.